once again. And then the other question is, well, when should I use that? You know, if I'm working on a startup, I don't have any issues of scale. I don't have any issues of code complexity. So should I really be using a microservice architecture to solve problems that I don't have yet? But then the problem you can run into is later on when you do have those problems, actually kind of refactoring into a service-oriented architecture, remodularizing your code can be kind of tricky and painful. So obviously people have done it, but it's not necessarily straightforward. So there's a lot of, you know, so on the one hand it's a really cool technical approach, but then there's some real complexity and pain associated with using it. All right, so that's kind of, any questions, by the way? Yeah.
So I see a lot of articles and on automation on the service side of things, but they just magically assume the UI can consume those services. And is there like a standard framework for on the UI that can consume this multiple services? And
ask me that question at the end of this section, because
okay.
it kind of touches on that. Yeah.
I was intrigued by your when to use it question, because I think that's something working in an enterprise IT shop, that's a question we often face, because a lot of things that the born on the web companies do, they are really architected for the web scale. But if you're developing something for the enterprise users, which probably number in hundreds or thousands or tens of thousands, but certainly not in the millions or
Yeah, I mean, you're sort of touching on a sort of real problem with thought leadership within software development. It's mostly led by consumer-oriented internet companies, the Facebooks, the Twitters, the Netflixes, who have to do things on a scale that most people don't. So yeah, I mean, it's kind of like you can get a lot of mileage out of a monolithic application talking to a relational database, using SSD drives versus a microservices application talking to a NoSQL database, right? It's just, you don't necessarily have the massive scalability problems. Yeah.
So sometimes when you split the monolith, there are areas that are actually common to most services. An example is authorization and authentication. How do you actually decide whether that becomes a service or it becomes a library? I see like sometimes you have to make a decision between whether it's a library that's statically linked versus a service that comes with a cost. How do you make that decision?
Yeah, that's it. That's sort of interesting. I mean, I don't have a precise answer to that, but I mean, so definitely you need to have libraries that are shared between different services, which is straightforward if those services are written in the same language, whereas if one's Java and the other one's JavaScript, you have a real problem. And and then other things, if you've got some service like, I think of authentication and it's maintaining data and state outside its own data and state, then it needs to be centralized and its own service and not embedded elsewhere. So yeah, it kind of all depends. Alrighty, let's move on. So now I kind of want to talk about the problem where I've broken up my app into all of these services and how do these services communicate with one another, and then also how do clients of those services communicate with them. So kind of a couple of different related areas. So, so this is the Amazon product details page, right? I think my book is actually, you can still buy a copy of my book there, though. Don't know why. But as I mentioned earlier, you look at Amazon's details page, there's all this information that you could imagine being pulled out of different services. So in the case of this simple online store, it's got product info, reviews, and recommendations, and each one of those pieces of information about a product is stored in a different service. So you've got some client of those services, which could be a server-side web application that spits out HTML, or it could be a mobile client, native client, or some app that's running inside the browser on a device. And they need to talk to those services to display the product details. So one option, of course, is that they could just access those services directly. You know, it's not, even though there could be hundreds of them, I guess they could be accessed over the internet. Except that that's a really chatty API. You know, there could be 50 calls just to get the information to display on one page. Not so bad on a LAN, but over a mobile network, that would seriously suck. And then maybe some of those services have protocols that aren't web-friendly. They don't want to go through firewalls and that kind of thing. So the solution there is rather than having clients talk directly to the back-end services, instead what you do is put in the middle an API gateway, kind of like a front-end server that the clients talk to, and then it talks to the back-end services. And that acts as a single entry point, and then provides APIs that could actually be specific to each client, and they would be web-friendly, or in some cases, so it can do things like protocol translation. So that for whatever reason, the review service has an AMQP messaging interface. Don't know why it would, but that doesn't go over the web, but the API gateway translates it into something that is web-friendly. And then, you know, a really interesting thing that this API gateway can do is provide APIs that are specific to a given client. So if you've got some front-end web application that's accessing the application over a LAN, high-speed, low-latency network, then it can just it can speak a chatty, fine-grained API, because that's just fine. Whereas if you've got some mobile app that's accessing the service over a mobile network, over the internet, in order for that to be efficient, you need to have a coarse-grained API. So the mobile app would just request the product details, and then the API gateway would call all of the relevant back-end services and gather up the product details and return them in one go. So just one round trip. And that's kind of really hugely important with dealing with mobile devices. And even there's an argument to be made that the web application, even though it's going over a LAN, maybe you should encapsulate the different partitioning of the services behind the API gateway, and so it just asks for product details and doesn't actually know which services are involved. So this kind of, plays a role of encapsulation as well. And Netflix have written quite a bit about that. They talk about, they're supporting a gazillion different kinds of devices, and their API gateway has device-specific APIs that just make life easier and more efficient for the client. And then it cools out to the underlying back-end services. So there are a whole bunch of challenges with building an API gateway, particularly at scale. So, you want to have like asynchronous event-driven I/O. There's also a challenge with dealing with partial failures because, maybe the recommendation service is down yet again. And so, you kind of have to recover from that and return the product details minus the recommendations so the page can just sort of mostly be rendered. So there's stuff you got to handle around that. And there's a whole bunch of technologies that you can use for building high-performance gateways. So on the JVM, there's Netty-based frameworks like Vertex or just Netty itself. Netflix have Hystrix for doing remote calls in a fault-tolerant way. And then in the system, I actually hacked together my API gateway using Node. Even though I hate JavaScript, but it just kind of is it's sort of well suited for simple things like the gateway. Okay, so then the other thing is, what if we've split up the web front end we've got lots of little web applications. How does the browser interact with all these different little web applications? And it's kind of the same sort of problem with the same solution as you kind of put like a API gateway, or so to speak, between the browser and the various web apps that just does routing based on the URL to the appropriate web application. So that's sort of another little piece. So the browser doesn't really know how your web application has been partitioned. Yeah?
So for the gateway, doesn't that add an extra coupler to your system? So every time you change an API in your service, now you also have to change your API gateway. Usually you would like to avoid that coupling in such a system, right?
Well, that's interesting. So a back-end service could actually, as part of it, the service discovery mechanism, could just say, I'm available and I support these URLs within the overall URL sort of namespace. So then when a request comes in, the API gateway can use the service discovery mechanism to figure out which back-end service to route that request to without it being hardwired into the gateway. I mean, like right now with my app, it's really simple. So my gateway just says, you know, /foo goes to this server, to this Docker-based service running on this port, /bar goes to that one, but ultimately there will be some fancy discovery mechanism so that it's all of the routing is data-driven.
Is the discovery being done all the time or just certain times? This comes up.
Yeah, I mean, you can poll. I mean, there's polling. I haven't figured out the details, but I mean, there's various sort of options, right? You cache the discovery, so you're not doing it on every request. That would make sense. Could be event-driven in some way. You know, cache invalidation based on events. Bunch of different options there. Yeah.
So, how do you think about the existing API management tool, like Mashally or
You know, I haven't really looked at them. If I were to guess, I would imagine they're kind of heavyweight. You know, in the sense that like my API gateway, it's actually doing a bunch of things, including OAuth authentication, but the actual routing is like 10 lines of JavaScript code. Yeah. So it's not a big complex task. But of course it's not doing kind of metrics or any, you know, I mean there's sort of, you could do something more elaborate, I guess. Alrighty, so then the other part of this is, well, how do these services communicate? And you know, there's a whole bunch of different options, right? So you have a synchronous protocol like HTTP, a messaging-based protocol. Then there's a whole bunch of different message formats, right? JSON, XML, protocol buffers, thrift format. And so there's a ton of different choices. You could say that kind of asynchronous is sort of preferred because it's got some benefits, but REST is hugely popular. And of course, JSON is really, really popular these days. But you know, a binary protocol is actually more efficient because you don't actually have to parse it. So there's a bunch of different ways, and people are doing it, you know, picking some combination. You know, messaging is quite nice because you don't actually have to do any discovery. You just talk to the message broker and say, send a message saying do this, and then the back end, you know, it gets routed to a back end service which the client doesn't know about, and if the back end service is down or unavailable or slow, the messaging broker buffers it up. So that's kind of nice. But you know, if you just want to do a request reply style pattern of communication, doing that over messaging is a little sort of a roundabout way of doing it. So, you know, HTTP or thrift is another option, and that's sort of, you know, simple request reply, straightforward, firewall friendly, which is good because you might be communicating with a native client. But then in some cases, you'd actually have, well, you have to know where the server is that you want to talk to. And, you know, in this sort of microservices world, and in the cloudy world, you need a service discovery mechanism in order to make that work, right? And that could be, one option of course is like using a load balancer. So the services register with a load balancer, the client talks to the load balancer that's on some well-known URL, and the load balancer routes to the appropriate instance. And so, you know, if you were using Amazon in a VPC, you could create an internal, non-publicly accessible load balancer to manage this. So that's another, you know. And then another option, which is say what Netflix have done, it's basically client-side service discovery. So the services register with a registry. In Netflix's case, it's Eureka, but other people use Zookeeper. And then the client asks the registry, where is the service, you know, where are the instances of the service? And the registry says what the hosts and port numbers are. So that's another option that's sort of, you know, this is quite popular, I guess. So this kind of the upshot is there's all these moving parts. We've gone from like simple monolithic system with a load balancer to like lots of services, API gateways, content routers, some kind of service registry to do discovery and so on. So it's all a bit complicated, but generally kind of worthwhile. All right, so kind of in the final part of the talk, kind of want to talk about decentralized data management, which actually sounds really boring and bland, but it kind of has a really big impact on actually the whole system architecture. And kind of the big motivation here is, well, you know, if we decompose the services, we've decomposed the database as well. In order for these services to be loosely coupled, really each service should have its own database. And so, you know, the order management service, which keeps track of orders, will have an order database. Customer management system will have a customer database. Means that they can evolve quite independently of one another. And you could imagine kind of having an architecture where one service might use a relational database, where another service might use Mongo, because you know Mongo is web scale and all that. Another one could use Cassandra. Another one could use Neo4j. So kind of got this whole polyglot persistence architecture, and it sounds great, except that you think about your database schema. It's actually really hard just to slice it up into independent things, because an order actually has a foreign key back to the customer, right? And customer OO terms, there's sort of a bidirectional relationship between the two. And so, in my example, I've got an order has a total, and a customer has a credit limit. And then there's a couple of invariants that need to be maintained during this at all times. So number one, the sum of the open orders must not exceed the customer's credit limit. So that means that in the order service, in order to place an order, you actually need information, you need the customer's credit limit in order to do that. And then likewise, a customer has a derived attribute, the available limit, that's the credit limit minus the sum of the open orders. And so in order to compute the available credit, you need to know what the available orders are in the order management system. So kind of when we split it up, there's this nasty relationship between the two that kind of gets in the way. And this is kind of the nature of the system, is that partitioning kind of doesn't exactly work at the database level, and so there's a bunch of problems you have to solve. So specifically, service A, in order to handle a request, needs to read data from service B, or you have to implement a transaction that actually updates data that's owned by multiple services. And that's a particularly hard problem to solve, because two-phase commit is sort of proper distributed transactions are not fashionable anymore. So there's sort of a bunch of challenges. So how can you handle reads? So one option is when you place the order, or when the order management system is processing an order, it can just go get the credit limit from the customer and do the check. So there's sort of the pull approach, right? And on the one hand, that's simple to implement, ensures you've got up-to-date data, but now the order service is dependent on the customer service being up. So we've kind of introduced this coupling, which increases latency and also can impact availability as well. So maybe that's not a good idea. The other option, of course, is the customer service can actually replicate the credit limit to the order management service. So the order management service no longer has to go out to the customer service in order to get it. So, you know, that seems weird because we all know that we're meant to use sort of normalized data, right? We shouldn't have these copies of data just sitting around. But, you know, one kind of sort of conceptual justification for this is in the book Domain-Driven Design by Eric Evans, there's a concept of a bounded context, which sort of says that, well, in one part of your system, you might have this thing called a customer, but that part of that sort of module's view of a customer could actually be wildly different from another view of a customer. So like, I don't know, order delivery is concerned about customers and their addresses, whereas kind of another part of the system might just be concerned with like customer care and how many times they've interacted with the company. You know, so marketing's view is different from the shipping system's view and so on. And so it's actually okay for different parts of your system to have different domain models where there's like a customer prime in one module and a customer double prime in another one, and they have the customer ID in common, but everything else is kind of different. So this kind of notion of replicating data is not such a bad idea, right? It kind of improves availability. It means that a service has the data it needs without having to call out to other services. But then the question is, okay, so how do we if we've got credit limits scattered throughout the system, how do we keep them synchronized? So it's sort of problem upon problem here. And so one option, of course, which is sort of a non-starter, is to use a distributed transaction. So when the customer management service changes its credit limit, it actually starts a distributed transaction that updates the order management service. And while that has kind of, from a developer's perspective, a nice simple programming model, from an operational perspective, using distributed transactions, you know, is complex, it impacts availability and so on. And for the most part, people don't use, you know, at scale, people don't build systems this way. And so that then leads to using an event-driven approach, where a service like the customer management service will just publish an event. The customer's credit limit has changed, and then the order management service will subscribe to that event and update its copy. So you've sort of got this eventual consistency model, which kind of is operationally simpler. It's a little more complicated from a developer's perspective, but it means that our systems are sort of nicely, loosely coupled. But then you've got the complexity of actually having to deal with eventual consistency, where, you know, you've got some transaction in progress and the changes haven't been fully replicated, and then you go and look at the data and it's actually inconsistent, and it's like things just aren't quite right, and you have to like try again in 50 milliseconds when hopefully those changes have propagated. So that's a sort of more complex programming model. And then whenever you're processing events, there's always the possibility of having duplicate events, which can sometimes be tricky to deal with. Like actually doing duplicate detection can be hard in some situations. So there's all this complexity around that. Though I think, to be fair, kind of this event-driven approach is kind of quite common. So then that sort of leads us to another question, sort of like the fourth question in a row, which is how do systems deal with it? How do systems publish an event? And the sort of the challenge is that you actually need to publish an event whenever the application state changes. But you have to do that atomically, right? Because you update the database, commit the database transaction, and then try and publish the event. Well, maybe between the commit and the publish, your server crashes, and you never publish the event, which means downstream the consumers will be out of date, which is sort of bad. And if you try and do it in any other order, there's a scenario where the database transaction actually gets rolled back, but you've published the event, and it's kind of tricky without using two-phase commit. So there's sort of two problems, like how do you generate events? How do you detect that things change? So you could do it at the database level. You could have a database trigger on the customer table that, quote, publishes an event whenever an update is executed against the customer table. I built a prototype where I was plugging into the ORM layer to do that. You could mix event publishing code into your business logic to say, hey, this has changed, published an event. So that's kind of messy. And then there's a couple of sort of domain-based approaches where you actually take an event-centric approach to designing your business logic so that events just naturally get processed. And I'll talk a little bit about that in a minute, particularly event sourcing, which is something I'm really interested in. And then the other part of it is, well, we've got an event and we need to publish it and update the database. And then it's like, well, how do we do that without using two-phase commit, which is sort of the thing that we're trying to avoid. And especially modern message brokers often don't support two-phase commit anyway. So, if you go back and look at eBay, which wrote about this 2009, I think, they actually used a two-step approach where the message store, kind of a quote, message broker, was implemented by using a database table in the same database that the business data was stored in, which meant that you could update the business data and publish an event by inserting it into an event table within the same local transaction. So you had a nice local ACID guarantee at that point that either both of them had happened or neither of them had happened. And then there was a separate process that was polling the event table and applying those changes sort of downstream atomically. And that sort of worked out really well. And that actually works really, really well in the SQL database, but not so much in the NoSQL database. But this two-step, eventually consistent approach is quite good. But what I've been interested in is this approach called event sourcing. And the big idea here is that you actually write your business logic in a totally event-centric way. So what's interesting, so a request comes in, HTTP request, you construct a command object like debit the account or change the credit limit, and then that gets sent to the customer aggregate. And the way the aggregate responds to a command is by generating, well, 0 or more events. So that processing the command doesn't change the state, it just gives you events back. And then you apply those events to the aggregate to update its state. So that's sort of the model. And then the other critical part of this is that you never persist the current state of the aggregate or entity. You actually persist the events. So, and if you want the current state, you just replay the events. So you kind of create a blank customer and then replay all of the events that capture all of the changes that have happened to that customer since the beginning of time to reconstitute the current state. So everything is event, so even your persistence mechanism is actually event-based. It's kind of like you've got an event store that's a combination of a database plus a message broker all at the same time. So graphically it looks like this. Request comes in, you want to update a particular entity, you go find its event, and then these slides are written in terms of an account, and then you apply the events to the account, or it could be customer, to reconstitute its current state. You process the command, which gives you some new events, and then you persist those events, which actually just get appended onto the events for that particular entity. And then what's really cool is on the other side, you can have another service that's subscribing to those events, and they get published by the event store, and then that event subscriber could then go and update some other entity that could be used to kind of update the copy of the customer in the order management service, or it could be used to update some other SQL database or text search engine that's providing a different view of the data. So when you're using this approach, it kind of looks like this. You got the customer management service publishes the customer credit limit updated event, which the order management service subscribes to so that it can update its version of the customer. So you kind of got this model where all these services are just like publishing events as things changed inside of them, and other services are listening to those events, processing them, which can generate more events. So events, just sort of everywhere. And it's, it's thoroughly event-centric. So like, this is what one of my domain objects looks like. So it's got two methods: process a command that maps a command into a sequence of events, and then apply an event that actually, this is an immutable domain model. So applying an event creates a copy of the entity which has been updated, so that you never update an entity in place. And then the underlying event store basically has methods like save new entity with the ID and a list of events, update an entity with some new events, and then loading an entity just gives you back a bunch of events which it then applies to reconstruct an existing entity. So it's all very, very event-centric. And it's kind of weird, right? But it solves a whole bunch of problems. No longer have to deal with any sort of OR mapping issues, right? Which have always been problematic. It actually works on top of SQL and NoSQL databases, and it lets you publish events in a very reliable fashion. And you basically get this eventually consistent mechanism. So it's kind of cool, but different. But then the other complication is that the event store only supports primary key-based lookup of entities. So if you want to do effectively joins, you end up having to maintain separate views of the data and writing code that denormalizes the stream of, you get a stream of events coming in, and it updates these denormalized view of the data that you can then query to support the UI. So for example, in the app I'm working on, I got text search. I want to do text search, and so I'm using AWS Cloud Search. So that's my view, and I have a service that's subscribing to entity change event that's then triggering the indexing of the document. And then I have another service that's running text queries against Cloud Search to support the REST API that's communicating back to the JavaScript client. So anyway, so that's kind of, it's a real interesting approach, and I'm sort of hoping to actually open source a big chunk of this, because I think it's useful.
Do you have fault tolerance? Kind of what happens if pieces of this thing go down and then you're losing events? So have you replicate them somehow, or do you have multiple?
Well, that's a really good question. So the event store, so you're assuming that the event store is fault tolerant, right? So then if a consumer, so basically the consumer is sort of like a persistent subscription. So like if it was AMQP, it would actually be, the kind of the model is you've got this named persistent queue that just like queues up the events until the consumer can consume them. So you could take a service offline for a day, and then when it came, like you took off the text search indexer offline, then when it reconnected, the system would say, well, I've got, here's 1,000 events for you to index, and it would just blast them at it. So, and then, so it sort of kind of works quite well. Services can kind of come up, go down, and because it's all message-based, nothing gets lost.
So how do you deal with the ever-growing list of events?
Disk is cheap.
Right, but if you have 1 billion events to process, wouldn't that take a long time?
Well, I guess the assumption is that you wouldn't be down long enough to...
No, but it's not just about being down, right? Because you always start, in your example, you had a new account, and you read the precedents.
Yeah. Oh, there's a ton of details. So you're right. So the handy analogy is like, if it was a bank account, you would see a stream, you'd see an open account event, and then you'd see a series of debits and credits, right? And I guess what you're saying is after n years, that's a mighty long list of events. So the solution is actually to periodically to take a snapshot of the current state of the entity and basically insert that into the event stream as a snapshot event.
I like it.
So that you then only have to go back as far as the most recent snapshot event and then load that and then replay forward. And, so it's just like every n events, every, whatever makes sense to optimize it.
You have to lock the row. You have to lock that object to do this, right?
Well, the scheme I have right now is actually optimistic locking. So when you load an entity, it's at version n, and then when you call update to append new events on, you just make sure that it's still at version n, and throw a optimistic lock exception if it's not, and then you can sort of retry that transaction.
You can also look at how big table handles the SS tables and compactifies them on the fly. You don't have to lock it.
Yeah, I mean under the implementation, this is implemented using ACA actors, and so it's sort of there's no sort of real locking other than some serialization around based on the actor queues.
The question, when you take a snapshot, right, you assume that thing will be in a consistent state, right? Then you take a snapshot. Otherwise, let's say even because you have one stream, right, event could be out of order. How you know there's a state you can take a consistent snapshot?
The events for an entity must always be in order. So if the whole model is load an entity at version n, generate some more events, you try and append those events, that will be you have to check that it's still at version n, right? Then so you're guaranteed that at that point there's a linear event stream.
Does that mean that these events are coming from a single service? Because you have to serialize somehow, right?
Well, the actual updating, so the events for a given entity are being generated by whatever service is handling the request, right? And so by virtue of implementing an optimistic locking check, you could actually have multiple services